Students, Dr. Hayes here, lecture 7, looking at chapters 1 and 2. Chapter 1 is on the chemical foundation, chemical history of how we got here to our understanding, modern understanding of the atom and then chemicals from that. A little warm-up question. Do you remember how many protons potassium has with the numbers here? Well, given these numbers here, turns out that the answer is, so you can write a symbol. We're going to get more into this later. I just wanted to see what you remembered. And let's see if I can get my pen to work here. There we go. So 19 is the number of protons. We write that there. Now, and then this number is the mass. That's protons plus neutrons. Anything to deal with number of electrons, we'll go up here in the upper right-hand corner, and the number of elements in a compound will go in the bottom right. But anyway, we'll get into that later. All right, this we want to get into now, chapter 1, chemical foundations. Just a few things. We're going to go very quickly, watch a little video, and then move on to chapter 2. What would I like you to learn from chapter 1? Learn something. Learn one thing, one person from chemical history. I'm going to show a little clip from a video. That would be something you can learn and memorize. The movie I'm going to show is Atom, Clash of Titans. But what I would like you to learn is a scientist. And you pick someone, first name, last name. Please know both of those. You're going to have to write this on a test. The time period they lived. When were they born? When did they die? And then what year did they make their contribution? Or what years? And then what was their contribution to chemistry? Not the world or engineering or the physics or the biology, chemistry. Has to deal with something with chemicals, okay? Yeah, because a lot of people may say Albert Einstein, and it's like theory of relativity. Okay, well, then you got to learn what years and that thing, but how does relativity deal with chemistry? So you're gonna have to show the connection. As you'll see, as you watch this today, there was some other things that Albert Einstein did that was directly related to chemistry. So he's one, and we're going to learn a few more. Okay, so remember, chemistry. You say, I don't know what chemistry is. Look in your textbook, look at this video, and look online, and you can find the answers to these questions. There's a wide variety of answers. This is your chance to find maybe a chemical superhero that you have. Okay, this will be on exam 1. It'll be one of the last questions on the last page. Practice exams are posted in Learning Hub, so you can go and see what the question will look like. All right, the goal for chapter 1 is just a little bit of the models that we have for the atom, and then we'll start applying that model to understanding the chemical makeup of an atom and the elements on the periodic table. If you're interested in more chemical history, I strongly recommend this book called Crucibles, The Story of Chemistry from Alchemy to Nuclear Fission. Great book. It really touched me when I read this as like a senior in college and trying to think about where I would go. And I found this to be very interesting to kind of give me the background. So maybe don't wait as long as I did and go look at that, check that out, and you can buy it online. I have a copy as well. And some great chapters on there. One of them on John Dalton, who did a lot to help us understand what atoms are. And there's some information in here about him. So John Dalton could be a guy that you write about. There was Antoine Lavoisier. I did a research to talk about him when I was a college student. He's a French scientist. And he said that, came up with the notion that when you're doing a chemical reaction, mass is neither created nor destroyed. So that has a lot to do with chemical reactions. It's just the atoms changing their arrangement. And there was Proust, who came up with this idea that compounds always contain the same ratio of elements in it. So water is always H2O. It's never H3O or H3O4 or some weird thing. It's always H2O. Before that, scientists didn't have an idea. Law of multiple proportions, saying that John Dalton came up with this. This underscored the idea that things are atoms. and they combine in whole number ratios, not fractions of things to fractions. So they always end up as whole ratios because it's always an element combining with another element and not fractions of themselves. And this gave us some strong evidence for atoms. At this time, we're going to watch a little video from the BBC called The Clash of Titans. Great video. I have the whole video on Learning Hub. Please watch it. You might be able to find it on YouTube, but here is about 10 minutes of it. We've got another person we can add into our list if we wanted to, and that's Ernest Rutherford. This famous experiment was in 1911, and here's a little picture of the setup. And so he was able to explain the nuclear atom and that it had a dense positive center to it, and the atom was made of mainly empty space, and electrons are on the outside somehow. So there, you can just memorize that for the test. That would be fantastic. Or maybe you want to find someone else. Of course, you need to add in the years that he lived. He was born in, yeah. So this began the modern view of the atom. And we know from other experiments that scientists did that there are also electrons. These are the tiny particles that are on the outside. These heavy, massive particles in the inside are protons and neutrons. So this is what chemistry uses to explain the properties of elements and compounds. Right. Further experiments have now gone on to find the mass of these three particles, as you can see here. The mass of an electron, 9 times 10 to the minus 31 kilograms, very tiny. So that's about 1,000 times smaller than the proton and neutron, which almost have identical masses. Probably the same with an experimental detail, or maybe not. And so, yeah, all the mass of an element, of an atom, is right in the middle. So how much more massive is the proton to the electron? I just divide the mass of the proton by the mass of the electron, and I get 1,800 times. So yeah, over 1,000 times more massive the proton is. So when it comes to the mass of elements, we just mainly look at the protons and neutrons. Electrons have mass, but it's negligible, usually within 3 or 4 significant digits. Another reason why significant digits are important. So we now are starting to learn that when atoms interact with each other, they are interacting with each other through the electrons on the outside. And so it's their electrons that bounce off of each other. And so because electrons define the outer surface of elements, electrons then become the key to understanding how they react, because these are the particles on the outside that interact with the outside world and other atoms. So how they exchange with each other or shared then becomes the key to understanding their properties. And that's what we're going to get into in chapter 2. How we understand electrons and their arrangement in elements. So just as a little bit of review or to help remember things, that the number of protons is called Z, it's called, well, the mass number, the total number of protons and neutrons is the letter A, and it's given in the upper left-hand superscript, and the number of protons is given as the bottom subscript on the left-hand side. Now, there's a little bit of what's called redundancy. If it's an element with 5 protons, it's boron. And boron has 5 elements, or 5 protons. So sometimes the element numbers of protons is dropped, and we just write the mass number. You can get different isotopes of elements where they have the same number of protons, but different numbers of neutrons. And so boron 10 has 5 protons, 5 neutrons. Boron 11 has 5 protons, 5 neutrons, or 6 neutrons. And so what's changing is the number of neutrons. So the identity of an element is the number of protons. However, how heavy it is depends on protons and neutrons. So how many electrons is boron 11 supposed to have? Let's see. Turns out to be 5. A neutral element will have the same number of electrons as protons. That will change depending on how the element reacts, but this is our starting point. Protons match electrons. Okay, we'll cover isotopes more in a later chapter. Okay. So that's it for chapter 1. Chapter 2 now, we're going to get started with that. Chapter 2 is on atomic structure and periodicity. Ooh, which said fall 2022. Guess I'm not able to write on here now. Well, 2022. Yep, a lot of the same things from last year, but some differences maybe. Shadow from, I'm gonna get rid of. There's a flame on a candle produces shadow. What do you think? Answer to that is no. Why does a flame not have a shadow? Well, here's a little video to show you.
Cast no shadow. Take a look at this picture. Do you notice something missing? That's right, there's no shadow. And no, that's not Peter Pan's candle. You also won't be able to sew one on with thread or rub it on with a bar of soap. To understand why, you need to know 2 things. 1, shadows are the result of light being blocked by an object. And 2, a flame is nothing more than a gaseous chemical reaction. Since light can pass through a flame unaltered and the flame itself projecting light onto the wall, there's usually no way for it to cast a shadow.
So light is very interesting in how it can pass through things. And it's our understanding of light that unveiled the inner workings of the arrangement of electrons in atoms. And so we're going to have to learn a little bit about light before we can understand electrons. And so that's the first part, chapter 2, that we're going to get into right now. All right, so how do we understand light? Well, we've got to understand electromagnetic radiation. Electromagnetic radiation is the energy of this entire spectrum that includes light. So we're going to look at the electromagnetic spectrum now. So we're not getting into other subatomic particles like quarks and boson, the Higgs boson, or any of those things. That's for physics, which is very valuable, but we're going to mainly just be dealing with electrons, protons, and neutrons. Okay, so light's going to give us the inner workings of the atom. Here's a little video about electromagnetic energy.
Something surrounds you, bombards you, some of which you can't see, touch, or even feel. Every day, everywhere you go. It is odorless and tasteless, yet you use it and depend on it every hour of every day. Without it, the world you know could not exist. What is it? Electromagnetic radiation. These waves spread across a spectrum from very short gamma rays to X-rays, ultraviolet rays, visible light waves, even longer infrared waves, microwaves, to radio waves which can measure longer than a mountain range. This spectrum is the foundation of the information age and of our modern world. Your radio, remote control, text message, television, microwave oven, even a doctor's X-ray, all depend on waves within the electromagnetic spectrum. Electromagnetic waves, or EM waves, are similar to ocean waves in that both are energy waves. They transmit energy. EM waves are produced by the vibration of charged particles and have electrical and magnetic properties. But unlike ocean waves that require water, EM waves travel through the vacuum of space at the constant speed of light. EM waves have crests and troughs like ocean waves. The distance between crests is the wavelength. While some EM wavelengths are very long and are measured in meters, many are tiny and are measured in billionths of a meter, nanometers. The number of these crests that pass a given point within 1 second is described as the frequency of the wave. One wave, or cycle, per second is called a hertz. Long EM waves, such as radio waves, have the lowest frequency and carry less energy. Adding energy increases the frequency of the wave and makes the wavelength shorter. Gamma rays are the shortest, highest energy waves in the spectrum. So, as you sit watching TV, Not only are there visible light waves from the TV striking your eyes, but also radio waves transmitting from a nearby station, and microwaves carrying cell phone calls and text messages, and waves from your neighbor's Wi-Fi, and GPS units in the cars driving by. There is a chaos of waves from all across the spectrum passing through your room right now. With all these waves around you, how can you possibly watch your TV show? Similar to tuning a radio to a specific radio station, our eyes are tuned to a specific region of the EM spectrum and can detect energy with wavelengths from 400 to 700 nanometers, the visible light region of the spectrum. Objects appear to have color because EM waves interact with their molecules. Some wavelengths in the visible spectrum are reflected, and other wavelengths are absorbed. This leaf looks green because EM waves interact with the chlorophyll molecules. Waves between 492 and 577 nanometers in length are reflected, and our eye interprets this as the leaf being green. Our eyes see the leaf as green, but cannot tell us anything about how the leaf reflects ultraviolet, microwave, or infrared waves. To learn more about the world around us, scientists and engineers have devised ways to enable us to see beyond that sliver of the EM spectrum called visible light. Data from multiple wavelengths help scientists study all kinds of amazing phenomena on Earth, from seasonal change to specific habitats. Everything around us emits, reflects, and absorbs EM radiation differently based on its composition. A graph showing these interactions across a region of the EM spectrum is called a spectral signature. Characteristic patterns, like fingerprints within the spectra, allow astronomers to identify an object's chemical composition and to determine such physical properties as temperature and density. NASA's Spitzer Space Telescope observed the presence of water and organic molecules in a galaxy 3.2 billion light-years away. Viewing our Sun in multiple wavelengths with the SOHO satellite allows scientists to study and understand sunspots that are associated with solar flares and eruptions harmful to satellites, astronauts, and communications here on Earth. We are constantly learning more about our world and universe by taking advantage of the unique information contained in the different waves across the EM spectrum.
Electromagnetic spectrum, it's that energy that has given us a detailed look inside of the atoms, not just of outer space, but deep inside. In fact, the new James Webb Space Telescope also utilizes the infrared spectrum to try to find molecular signatures of what it's going to try to look at is the atmospheres of different planets as they transit around their suns. The key thing here that we want to look at now is know that electromagnetic energy has two key components, wavelength and frequency. And together, the wavelength and frequency are moving through space at a certain speed. So that is the speed of light. And this comes across in a formula I would like you to learn. The speed of light is equal to the wavelength, and this has to be in specific units, in meters, times the frequency of that light, which will be given in, not meters per second, but in just 1 seconds. So the units of light will be in meters per second. So meter times per second is creates an equal equation here. So we have the same units on both sides. So when we're using this equation, we want to make sure wavelength is in meters, frequency is given in 1 second or hertz. A hertz is defined as 1/s, 1 seconds. The speed of light to 5 significant digits is 2.9979 times 10 to the 8th meters per second. So we're always going to know this number. And what's going to change is the wavelength and frequency. So let's look at that and some problems here and some relationships to light and others. I've got the speed of light is an errorless number with infinite significant digits. The answer is false. It is a measurement. Scientists do measurements to get to this number. So that's why that's 5 significant digits. And so we want to make sure we understand that. Okay, so here's the big equation. And I've rearranged it a little bit. So it was speed of light equals lambda times nu frequency. Those are the name of the Greek letters that we're using here. So if I divide both sides by lambda, I can find out what nu is. What is nu? You're going to now say C over lambda. What's nu? Get it? What's nu? Isn't that funny? Kind of. All right. I thought it was kind of clever. I actually put it on a t-shirt. I'll wear it when I see you guys again. All right. All right. Getting back to the message at hand here, the nature of waves. Now, waves, from the electromagnetic spectrum, have these two qualities: wavelength, okay, the distance between the amplitudes there, and then how fast those amplitudes are going past you. That's frequency in hertz. And it's strange, but then all of them are moving through space. Now, my little analogy here is that imagine a truck or a car kind of bouncing through space here, but they're bouncing up and down, like with really bad shock systems. And so something like a purple truck would be going through at 60 miles an hour, but it's vibrating up and down. So that's the frequency. And it's kind of big. So I use the big one for the purple for a reason, because it has the purpler colors, because the blue end of the visible spectrum have more energy. We'll show that in just a moment. And then as you go from blue to green, the yellow, orange, and red, the energy of those waves decreases. Okay, and so that's associated with the wavelengths getting longer and the frequency getting slower. And so we can recognize some of that with this equation, like the speed of light, how fast they're all going the same speed, but they have different colors. That's the wavelength, and then different frequencies. All right, now let's take a look at the entire electromagnetic spectrum, all the way from gamma rays to radio waves. And gamma rays have the shortest wavelengths, 10 to the minus 12 meters. And that is important to know. So I want you guys to memorize that. And then the wavelengths get a little longer as we go to X-rays, and then the UV, visible, infrared, microwaves, and then just radio waves. I'd like you to memorize those regions in that order there, from shortest to longest. Now, kind of in the middle-ish is the visible spectrum. And that visible spectrum is in a very important area. It's from 400 nanometers to 700 nanometers. Blue wavelengths and purple are around 400, and then reddish is around 700. Also memorize those two numbers. Those are key because that's where our detectors, our visible detectors, work. Let's practice doing some conversions here and some sample problems. Let's say you have a wavelength of 700 nanometers. Let's go ahead and calculate the frequency that's associated with that. So recall from our little formulas that C equals lambda times nu. And you can use what's nu, nu equals C over lambda. Either one will work here. It just depends on what you want to start with. Now, in order to use this formula, we have to now convert 700 nanometers, the red light, into meters. From our conversion factors, we remember the perfect conversion factor, 1 nanometer is 10 to the minus 9 meters. So I multiply them, my nanometers cancel out, and I have 7.00 times 10 to the minus 7. Now, this looks like it's only 1 sig dig. I'm going to make it 3. Ta-da, it's 3. And so there we go. 7.00 times 10 to the minus 7 meters. So now, knowing our little formula that we talked about here, we can plug in. So I'm going to go ahead and use this one. We can plug in the speed of light, 3.00 times 10 to the 8th. You say, well, why don't you use more significant digits? And you can, go ahead. But I'm only going to be limited to 3 because of my other number, the wavelength. And then I can divide the speed of light, meters per second, divided by meters. Now I'll get my meters to cancel out. And I'm left with a 1/2 for the unit, a hertz. So my calculator tells me 4.29 times 10 to the 14th. So check that out, make sure you're getting that number. Speed of light divided by the wavelength in meters. Then you get your answer. Okay, moving on. Now also understand something about the energy of this light. The unit of energy that we're going to use is called joules. Joules can be broken down into some other units that we're going to learn at some point, where we're going to learn a little bit right now. And there is a SI International Units definition of energy, the joule. It is equal to a kilogram meter squared per second squared. We're going to need this definition in some of our problems in this chapter. So a joule is really kind of like something moving, a mass times the speed of light squared. And so we want to remember this is where energy gets its light, is from this kind of thinking right here. So just joules for now, and know that it represents, it can be equivalent to mass and speed of light. So we want to memorize that conversion factor. I usually give it to you, but if you kind of know that there's an equivalency out there, it'll really help. Okay. Einstein, now here's Einstein again. He did a very interesting experiment in 1905. He described what's called this photoelectric effect. And this helped scientists understand the relationship of energy to light. And what he showed was that by shining certain colors of light, he could trigger a photoelectric effect. What's that? Well, with certain colors of light, he could get the electrons of certain metals to kind of kick off and cause an electric current to occur. However, this would only work with certain colors of light. And from this, he hypothesized that you can't just take any old color of light you want and then turn up the intensity of it, that it's light itself that comes with packets of energy, is how he thought about it. And because of this packet of energy idea, this started the revolution of quantum energy, that light was quantized into these little packets of energy. And if they weren't of the right type, you couldn't kick electrons off. Very important idea. And so there's Einstein's contribution to science, or not to science, but the science, but at the chemistry. And because of this, he developed a little formula that said, yeah, the energy of a photon of light, these little packets he called photons, they're massless packets of light. He said the energy of that is related to the frequency. And it was related by a constant called Planck's constant. And then here it is, 6.626 times 10 to the minus 34 joules. There's an energy times second. And if you multiply that by the frequency, whatever the frequency of light, we can figure out how much energy is there. Now, because of the definition of what's new, remember what's new, C over lambda, we could substitute C over lambda in there and also get another interesting relationship that shows that the energy is inversely related to the wavelength. All right, thanks for hanging in there, guys. We're almost done with this lesson. This one's a longer one. And all right, so this transformed the idea that waves of light also have particle nature to them. All right, and so yeah, so Einstein kind of gave us this idea of particulates of light. And so I'm going to just kind of go on to this next slide here, kind of move on. And so what we can start learning from this energy relationship is that wavelengths on the red side of the spectrum, going from infrared to microwave wave, those get lower in energy. There's an inverse relationship. And as the wavelengths get smaller, there is a larger energy. So gamma and X-rays and UV are very energetic. They have lots of energy. In fact, they split chemical bonds. Infrared and microwaves, they cannot split bonds. They don't have the right amount of energy. So what about visible light? Which color has the greatest energy? Green, yellow, or orange? What do you think of those three? Yeah, it turns out green, because green is closer to the blue side than yellow and orange. So this has the greater energy, and this has low energy on this side. All right, I think we're going to try to get to one last problem here. So to summarize, what do we learn so far? Long wavelengths, they have small frequencies and low energies, but interesting enough, they can travel further through materials. Bluer colors into the UV and X-ray and gamma rays, they have high frequencies, high energies, and they're absorbed by more materials. And I can tell you right now that they do a lot to initiate chemical changes because they typically break chemicals. All right, we've been going for almost 50 minutes, and I want to just bring this to an end because this is a class period here. All right, so here's how you can remember, right? This little color wheel, and you can see some individual colors here. Going from low energy to high energy is from red to purple. All right, so add one calculation that we're going to do, and that will be it for this one. Let's calculate the energy. What? No, what's one? This is calculating the frequency at which a local AM radio is broadcasting. Oh, so this is going to take a frequency, 575 kilohertz, and we're going to find the wavelength. Oh, so this isn't an energy calculation. This is actually looking at the relationship, once again, between lambda and frequency and the speed of light, because there's nothing about energy here. We could turn it into an energy one. All right, so let's practice real quick. Okay, what do we got? Frequency, 575 kilohertz, and we know the speed of light because we always know what that is. So we're just going to plug in the frequency, and we are going to calculate and plug in C and then solve for lambda. But in order to do this, we got to make sure the units are correct. We know that wavelengths have to be in meters, but what do frequencies have to be converted to? And the answer is 1/seconds. So since this was done in kilohertz, there's a conversion factor because if you remember, kilo is 10 to the third. So there's 10 to the third seconds in 10 to the third seconds in 1 kilohertz. So I can set up a conversion factor that says 575 times 1 kilohertz times 1,000 is 1,000 hertz. And if you want to get fancy, you can just say 1 hertz is equal to 1 inverse second. And so we can get to our specified units here. So now I know what the frequency is. And then that one I can now plug into our formula where lambda is now equal to speed of light divided by frequency. So plug those numbers in and figure out the wavelength is 521 meters. Whoa, that's long. That's like thousands of feet long. And that's what radio waves are. They're really long wavelengths. All right, so I think we're going to, the units. How did the units work out? Well, they work out when I have speed of light, meters per second, and I divide it by 1/seconds. And so this is kind of confusing. So how did I get that? Well, remember, dividing is multiplying by the reciprocal. So if I multiply by the reciprocal, that's just seconds cancel out and we're good. So we're going to end it here. We've been going long enough. That's a class period, and we'll pick it up on lecture 8 here coming up next. Thanks for hanging in there, and we'll see you next time.